Can the uncertainty principle be used to improve our understanding of quantum mechanics? What if I tell you and show you that there is another kind of uncertainty principle that exists other than Heisenberg's uncertainty principle? Is it possible that the uncertainty principle and the Fourier transform provide us with a deeper understanding of the interconnectedness of the quantum world? How do the uncertainty principle and its connection to the Fourier transform challenge our classical intuition and pave the way for a new perspective to reality? Well, in this video I'm going to answer all these questions and show you the deep underlying meaning of what is the uncertainty principle, its real meaning, and its connection to something very fundamental to wave mechanics, Fourier transform. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to this fresh new video, Uncertainty Principle and Fourier Transform. Well, before we start going into the details, why don't we look into something very original? How Heisenberg coined the term. Did he coin the term uncertainty or something else? Let us look into this. Well, I would not pronounce this word because this is a German word, but if I take an English translation, it means inexactness. And Heisenberg used this another word in order to means undeterminedness. Although this is a wrong English, but just I'm giving this to make you understand. Now, if you take the word in a literal sense, inexactness, it refers to the lack of precision or accuracy in a measurement, calculation, or representation. So it implies that the value or information being communicated is not exact or completely precise. Whereas if I take the word uncertainty, it refers to the lack of knowledge or information about a particular event, outcome, or measurement. It implies that the true value or outcome is unknown or cannot be precisely determined. So you see, fundamentally there is, even in English terms, there is a difference. Inexactness refers to the lack of precision, whereas uncertainty refers to lack of knowledge. However, once we come across Heisenberg's uncertainty principle, the definition tells us that there is an absolute limit on the combined accuracy of certain pairs of simultaneous relative measurements, especially the position and the moment of a particle. First, we would like to go in the traditional way and let us understand, just in simple words, without too much of complex mathematics, what is the uncertainty principle, and then we will go something amazing to discover a link between these two. So we generally denote this one as delta x, that means uncertainty in position, and delta p as uncertainty in momentum, which is always greater than equal to h bar upon 2, which is a Planck's constant. There's something not much to explain about it. So what does it imply? That if I make the delta x very small, then I have to make delta p very big. The reason is that it has to be greater than equal to some number. So if I take a particular subatomic particle in a classical world, and if I plot it, I can say that we know exactly where the particle is located. If I take a quantum realm and plot the same xy axis, then I get this blue curve, which is a kind of a probability distribution, and this delta x shows that the particle can be here, 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 or anywhere. So the position and the velocity of an object cannot be both measured exactly at the same time. So this is the way in general when we talk of the uncertainty principle in the quantum realm or otherwise we come to know. But I would like to tell you, this is not the exact definition, or this is not the right way. Now, in order to know a little bit about that, we have to turn the pages of history and go back to 1768 to meet this wonderful person and know a little bit about him. Jean-Baptiste Joseph Fourier, French mathematician and physicist born in Auxerre and best known for initiating the investigation of Fourier series, which eventually developed into Fourier and harmonic analysis. Fourier accompanied Napoleon Bonaparte on his Egyptian expedition in 1798 as a scientific advisor and was appointed secretary of Institut d'Egypte. In 1822, Fourier published his work on heat flow in the analytical theory of heat, in which he based his reasoning on Newton's law of cooling. Fourier made important contributions to dimensional analysis, and other physical contribution Fourier's include partial differential equation for the conductive diffusion of heat, which is actually an equation now taught to every student of mathematical physics. Well, this is more or less we come to know about Fourier. Now let us come to what actually is the Fourier transform, not in a very difficult mathematics. I will lay it down very easily to you. So if I take the definition at itself, it tells that the Fourier transform is a transform, obviously, that converts a function into a form that describes the frequencies present in the original function. So what do I mean by that? This is the one. So Fourier transform is basically a mathematical tool. As you can see on the screen, it breaks down a signal into its individual frequency components, revealing the different frequencies present within it, and it has got immense amount of implications in signal processing, data processing, many other things. Anyway, so let me give you a visual understanding of what is a Fourier transform. Consider this to be a music playing. Whatever, it can be a single note, it can be anything. Now what Fourier transform actually does is that you see this one, the curvy length or this wiggling wave, whatever it does, it actually does that it takes the music and decomposes it into constituent frequencies or notes. This is exactly the role of Fourier transform. We will come to how it is related to Heisenberg's uncertainty principle, but before that I'm coming to make you understand it in a graphical manner. So if you take this arrow, say for example I take it as a vector, right? We know that a vector can be broke down into components vector, so I can make this blue arrow break down into 1, 2 and 3 components, right? And then we can add it up into a single vector. If I take this kind of a frequency, which is for example it has got a frequency of 5. Now what happens is that typically when we Fourier transform it, I make another wave which is obviously of different frequency. I take it, say for example, two components, 2 frequency, and then I got another of 3 frequency, and I together add it, and what I do is this one, I Fourier transform it. So what I'm trying to make a point over here is that when I am doing a kind of a Fourier transform of one of the equation, then the original equation gets Fourier transformed into the second one. So this is typically the function or the rule of Fourier transform. I will try to demonstrate it in terms of frequency and time in the next diagram. Now say for example I have got this kind of a graph, right? This goes in the x direction, I plot it as time. This goes in the y direction, I plot it as frequency. And I've got a lot of, wiggling waves where I know that this particular, and this on the right hand side there is another one which have got a very very high frequency intensity. So if I plot those red dots, what I'm trying to tell you is that these are the points where I exactly know my specific time, or in technical terms I can tell about the temporal information, because you see that any point of time I can point this red dot, or wherever I am in this frequency distribution, I can tell that I'm here or here or here. But the problem is that I don't know anything about frequency, right? Now in order to know from this graph, the left hand side to the right hand side, I want to know the frequency, so I Fourier transform it. So what I get is this one. Now here I have got a lot of frequency. You can see these are, crests are going quite up and they're sharp. So I know a lot about the frequency resolution, but the problem is that I don't have any temporal information. That means I really don't know anything about time. So this is kind of a trade-off which is coming. Let me show you further. So this is a pictorial description of what is the Fourier transform. Let me show you further. So I take both the graphs, right, where I've got I know where is the time, and exactly I can denote, and I know here I know the frequency, but I cannot plot out the time. So these are the red dots which informs that this is the time and this is where the frequency is. Now the question that comes is that can I arbitrarily get high frequency resolution as well as temporal resolution? That means I want to know both about this one, the left hand side arrow, as well as the right one, the right hand side arrow. So I really, as a physicist, I will always try to get the exact information, isn't it? So I would like to know an arbitrarily high frequency. That means I want to know the frequency as well as I want to know the arbitrarily exact time where that frequency is occurred. So the answer is this: no, there is always a trade-off. right? So now I think you are already getting a kind of a intuitive answer how it is related to Heisenberg's uncertainty principle, because these always occur in conjugate variables, which is the same in Heisenberg's uncertainty principle. So what would be the way? Can I get a kind of a trade-off where there is an average? No, there is always a trade-off, but still we have something called spectrogram. This figure shows this. So this spectrogram actually is a fundamental trade-off, as you can see on the left hand side, between how much resolution I have in frequency and how much resolution I have in time. So it shows that the changing the number of data points used for each Fourier transforms block, the spectrogram loses definition in the frequency of the time. So this is important. So when I am changing the data points, you see, now this has got nothing to know about quantum mechanics, right? We are not into quantum physics or any electron, proton or subatomic. This is just pure sound waves or any kind of a wave mechanics that we are trying to explore, right? So it loses the definition of frequency in the time. So this spectrogram, which is right in front of you, is actually a trade-off where you're getting a kind of an average between resolution I have in frequency, how much I have in time, but there is always a trade-off. The question is that, can we show this in terms of a mathematical equation? I will just show you with a very simple example. So I will do a kind of an integration with the entire range from minus infinity to plus infinity with a square of the magnitude followed by dx, and I will Fourier transform it on the right hand side with a d omega, and this would be always greater than equals to 1 upon 16 pi square. Now don't ask me what is 1 upon 16 pi square. This would require another video because I have to show the derivation for Fourier transform, not required at this moment. This is what we call the second moment of that function, and this is multiplying it with the same measure but its Fourier transform. Now this seems to be trivial because anybody who has done a Fourier transform can understand this equation, and you can mathematically derive through your mathematics. But what is very fundamental is this one. So if you try to localize, I mean to say this equation is both in space or in time. I have not mentioned it. So if you try to localize wherever you are located in space or time, obviously this function would be a Gaussian, and the Fourier transform will obviously another Gaussian. So if I'm trying to localize wherever I am in space or time, the Fourier transform will always be spread out. Because the product has to be greater than this one, 1 upon 16 pi square. So this is a very fundamental understanding. You see, we have not, we haven't done anything related to quantum mechanics, but it's just that the signal and how the Fourier transform. So if I'm trying to localize where I am in terms of space of time, as soon as I Fourier transform, because I need the other information, it will be the probability distribution, the dispersion will be more and it will be spread out. One note of caution is that I have seen in internet and otherwise this equation and this equation you might come across, but both of them are the same. Here it has been used as x minus x0 squared with a xi sign, and this is done by omega. So anyway, I just wanted to make you understand that don't get confused, both of them are the same. So now we come back to this equation, and this is called the uncertainty principle. Remember, this is also an uncertainty principle, which I told you I will show you at the beginning of the video, and I will make you understand. So the left hand side, if I'm making it very tight, I am taking a kind of a very tight distribution of the Gaussian function, and what I'm getting is this going up. Right, so I have got a lot of frequency. Right now, I want to measure the time. So I Fourier transform it, right, and what I get is this one. See, this is spread out. Why it is spread out? Obviously because the product has to be greater than equal to 1 upon 16 pi squared. So the tighter is my distribution of one of those variables, the broader the distribution, or you can say the broader the uncertainty will be on the other variable. Vice versa, so the Fourier transform of a Gaussian is another Gaussian. Vice versa, if I take a tight kind of a distribution where I'm trying to squeeze and find out a particular a frequency or a temporal time, then obviously on the left hand side again it will be quite spread out. Right, so you already got an intuitive understanding. So in a better picture, I can say that the Fourier transform, the original function, if it has got a spike, that means if I'm certain here, I know the frequency, right? Then the Fourier transform will be uncertain over here. Why? Because the probability distribution is a huge curve and the electron can be here, 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 anywhere, right? And if I am uncertain over here because the probability distribution is quite big, that means I will be certain over here, right? Now in mathematically, which part of the equation spreads out? Let me show you in the next part of the video. So I've taken both these equations. The more concentrated f of x are is, the more spread out would be either f of xi or f which has got a hat over omega. This must be, right? If we squeeze the function x, its Fourier transform will stretch out to xi or omega, whatever the variable, doesn't matter, right? So I have just underlined that in red. So this shows the uncertainty principle in terms of Fourier transform of any wave mechanics which is applicable. Now the question that might be going on in your mind is that we have understood Fourier transform, we have understood how it is related and how one leads to a trade-off with other. The question is that how this is connected to the Heisenberg's uncertainty principle. So enter quantum realm. So the connection of Fourier transform of uncertainty. So you see, Fourier transform is what? It is I would say uncertainty relation between position and momentum arises because the expression of the wave functions are in Hilbert space. So again I have taken a sound wave, a pure tone. It has got a sharp spike, very sharp spike at a single frequency. Again, if I Fourier transform it, it gets completely delocalized as a sine wave. Now here comes an important catch. If I take, as we know that everything in quantum physics is defined by what we call is a wave function denoted by the Greek letter psi. So here is a catch. The wave function for a particle's momentum is always the Fourier transform of the particle's position, right? So if I take the wave function, right, of a particle's momentum, if I Fourier transform it, it will be particle's position. Let me show in a pictorial description. So here is the graph, which is the original function. It is a wider function, so lot of distribution. I Fourier transform it, I get a narrower Fourier transform. I get a wider function and it has got a wide range of area. That means probabilities wave function has got a wider area. That means probability distribution is quite wide. Uncertainty is more. Again, if I Fourier transform it, it will be narrow. So here it is. Wave function for the particle's momentum is narrow, and if it is narrow, then it will be wide. So coming back to Heisenberg's uncertainty principle, if you know less about the particle's position, you see the probability distribution is wide. So obviously the particle's position I cannot know. In order to know, I will be Fourier transforming it and I will get something about the momentum. Again, if I know more about the position, which is a narrow kind of a Gaussian function, I will get which is less about the momentum, and this is actually depicted as delta x delta p greater than equal to h bar upon t. So that is actually the basic connection between Fourier transform, the uncertainty which exists in a Fourier transform combined with the uncertainty principle which exists between in the Heisenberg's uncertainty principle. Okay, so a lot of mathematics till now. Let us summarize in a simple language. So what we can do is that we can say that when there is a high probability that a particle is going to be measured in a small region, there is a low probability that it will be measured within a small momentum range, since the momentum probability is spread out. So Heisenberg's uncertainty principle, which states there is a fundamental limit to how precisely we can measure certain pair of properties. So more precisely we try to measure on one property, the larger the uncertainty or variability. So we can say even that if you really have a fine peaked information, that means the peak is quite high, just I have shown about your spatial distribution, you will have an uncertainty inherent in the Fourier transform and vice versa. So the uncertainty principle, remember, comes up not only in quantum mechanics but also in signal processing and any part of wave mechanics. So this is something we can tell. However, we have got few more misconception. Quickly I will just summarize. So in the summary, what we can tell is misconception number 1, uncertainty principle is caused by experimental disturbances. Some people mistakenly think so, but it is actually not. there, as some people think, because of a technical limitation, but the uncertainty principle is not caused by external factors, but it is an inherent property of quantum systems. We have seen that it arises from the wave particle duality and the mathematical relationships between the position, momentum, wave function. The second misconception is that uncertainty principle implies that particles do not have properties until observed. Absolutely not. While the uncertainty principle introduces inherent limits to our knowledge of certain properties of particles, it does not imply that particles do not possess definite properties. The properties of particles exist in a state of superposition where they can exhibit multiple possible values simultaneously. However, when a measurement is made, the wave function collapses and the particle assumes a definite value which is being measured. So this is another kind of a misconception. Misconception number 3 is the uncertainty principle violates classical notion of determinism. No, classical physics is based on deterministic principles where the properties of particles can be precisely known and predicted. Now, the uncertainty principle, on the other hand, introduces intrinsic limitations to the simultaneous measurements of certain properties in the quantum world. It does not necessarily violate determinism, but highlights the probabilistic nature of quantum mechanics, where the predictions are made in terms of probabilities rather than certainties. Lastly, I would like to tell, some people think that uncertainty principle is a result of a lack of knowledge of technological advancement. No, uncertainty principle is not a consequence of a lack of technological advancement. It is an advancement principle, fundamental principle that arises from the mathematical formalism of quantum mechanics and has been experimentally confirmed many times through various experiments. Advances in technology can improve measurement precision but cannot eliminate the inherent uncertainty which we have found in the Fourier transform. So that completes our discussion, the relation between Fourier transform, the uncertainty which exists in any kind of a wave mechanism, and how to conjugate variables and the Gaussian function, we got it similar to Heisenberg's uncertainty principle. So I think now when you will be facing Heisenberg's uncertainty principle, not just it is a position or a momentum, you can think much more deeply. So finally, I have summarized in these few lines, we have truly understood the meaning of uncertainty principle. There is an uncertainty in the fundamental idea of any wave mechanics, Fourier transform, and how Heisenberg's uncertainty principles are linked. Uncertainty is not only for quantum world but also in wave mechanics, and we have seen position, momentum along with the Gaussian function, how Fourier transform is now clear. So that's it. I'm thankful for those who have watched my video. Please do subscribe to my channel Physics for Students. Click on the bell icon to get all the notification from Physics for Students. For any clarification, you can contact me at this email ID. I also have a specialized channel dedicated to Einstein's general theory of relativity, which you can subscribe. Further, you can follow me on my Instagram, Facebook and LinkedIn pages. So please do let me know, how do you feel, what are your feedback about this video. I will be waiting for that, and Physics for Students will be soon back with much more interesting videos on quantum mechanics and various other subjects. Till then, goodbye.